before solving for a periodic trajectory or for a time domain simulation or for linearization and frequency lifting, calculation of eigenvalues, calculation of frequency responses, I need to define inputs. So this is again something that I can do by giving the harmonic spectrum of all input variables. I see that the alternating voltage is defined as a sine wave with this parameter as amplitude. The direct voltage is defined as just a constant value. This is for the index 0 Fourier coefficients, and this reference for the alternating current, I define it again as the fundamental frequency Fourier coefficients, still as a sine wave and with this parameter as amplitude. This time I don't want to let the solver search from 0 because they're in more elaborate systems, starting from 0 may imply that there are divisions by 0, which leads to errors. So what I do is that I will help the collocation method find the steady state periodic trajectory by giving it non-zero values. It could be anything as long as it is non-zero. It is supposed to work, but I can help it even further by giving values. In particular, I know that the circulating current will not be too far from this value. I know that the upper arm and lower arm sum capacitor voltages will not be too far from the rated voltage, and so on. So now that I have defined these inputs and these initial guesses, I can solve the collocation method. Going back to the main, I am happy to solve up to harmonic rank 6. This is generally a sufficient value for the MMC, unless you have additional harmonic disturbances on the inputs. I am still working with the numerical Jacobian, but later we will try also with the analytical version of the Jacobian. I am defining inputs from the user-defined file, which is the one that I just showed you. Initial guesses also from the same file. I will not change the tolerance of the algorithm and keep the same number of points in the resulting waveforms. I'm running this part of the code. I have again the eigenvalues of the Jacobian. It is a non-delayed system, so I can trust these eigenvalues to provide me information about stability. I see that in this particular case, the periodic trajectory that has been calculated by the collocation method is stable. Also, I see the absolute error at the end of the collocation calculation. It is maximum 10 to the minus 13, which is a very small value. So all the unknowns, which you can see here, there are more unknowns than with the simple RLC system. All the unknown variables have converged to a very small error. Additionally, I see that the residual, as stated by the Levenberg-Marquardt methods, is very small, that the equation is solved. This is a good news, and that a very small time has been necessary to solve for the periodic trajectory. As usual, I can find the results of the collocation method in the HT structure. I have one of such structure, harmonic data, given by the collocation method corresponding to one fundamental period. I see that we have 13 Fourier coefficients, which makes sense because we solve up to harmonic 6. So we have 6 coefficients for the positive frequencies, 6 coefficients for the negative frequencies, and 1 index 0 Fourier coefficients. That is a total of 13. Those are the ones that we have defined ourselves. So this is the vector of this is the vector that we have defined for the alternating voltage. We have the minus the negative fundamental frequency and the positive fundamental frequency. I can also have a look, which is an easy check at the harmonic spectrum for the direct voltage, it is indeed just a constant value, and all the rest is equal to 0 for negative frequencies and positive frequencies. I see that this time I have a vector of frequency values covering everything from minus 300 Hz to plus 300 Hz. I have a total of 13 Fourier coefficients, as mentioned earlier, and that the base frequency is this time 50 Hz. This is indeed what I have defined both in the data file. F1 is defined as 50 Hz, but also in the harmonic domain data. The fundamental frequency is set as 50 Hz. Meaning that when I say minus 1 and plus 1, in this vector of Fourier coefficients, this corresponds to minus 50 Hz and plus 50 Hz. Okay, I have also the results for the states, so for the circuit and for the controller, as well as additional results for all the outputs that I have requested. So this is not just harmonic spectra, the corresponding time domain results are available in this structure. Time domain data given by the collocation method over one fundamental period. I have the time vector and the data points for all the variables of interest. I can plot all of these with the same plot function as before. Control D to open it directly from here. So naturally this will not work because those were the variables from the simple RLC circuits. But if I use this code snippet, I can directly obtain the list of variables for this MMC. I do F9 after having selected the line to run it in the command window. I can copy paste the provided list here, and now let's say I would like to see the results of the collocation method, the waveform of the collocation method for the alternating current. I run it and I have the results. I would like to have just a normal line, and there it is. I would like to see at the same time the two, so the upper arm and lower arm sum capacitor voltages. I run it, and here is the result. I can observe the four of these states together by running again. And I see indeed in blue the alternating current, in red the circulating current, which is almost constant with a small harmonic component. And I see the two sum capacitor voltages near, just with a ripple around a constant value. So the reason why it is scaled around 2.5 is that I am not actually using per unit, but I am just scaling the system such as all the variables are reasonably close to 0. However, you know, per unitizing the MMC may imply using different bases for different variables. To simplify this operation, I use the same set of scaling variables for all variables of one same MMC. So if I wanted to obtain the actual values for the sum capacitor voltages, I would have to multiply these ones with the base value that I use, and actually this is the one that I can find here, VA base for the MMC. Okay, in any case, I can do as before, not only check the time domain waveforms, but also the harmonic spectra. I see that I have the data up to 300 Hz. This is for the lower arm sum capacitor voltage. I can zoom on its harmonic content. Same thing for the upper arms sum capacitor voltage, the circulating current. We saw that it is mostly constant, but it has a, for this particular example, a 200 Hz component, as well as much smaller 300 Hz component. Naturally, the alternating current is essentially a fundamental frequency waveform, but it does have some 150 Hz component. I recall that this is a single phase MMC. So you can technically have a look at all the variables that you want. Let's say out of curiosity, we can have a look at the instantaneous power. This is its spectrum. I can also have a look at its time domain waveform. This is what it looks like. Again, this is normal to have this as instantaneous power since we are working with a single phase converter. The advantage of using sets is that I could define, let's say, these 4 variables together. And I would like to have my 2 control states related to the alternating current, and then I would like to also see as a third set of variables the upper arm and lower arm modulation indices. Okay, so I have in a variable sets in this cell, I have 3 sets which I have defined myself. This is something you can do however you want. So if I want to see anything, naturally I have to tell the Toolbox what I want to see. I would like to see the results of the collocation method in the time domain. So this is what I can do. So I have the set of those modulation indices, upper arm and lower arm, the control states related to the alternating current, and again, 4 of the states related to the circuit. Just as before, you can do other things such as having harmonic disturbances defined in the harmonic domain. For instance, you can have a disturbance on the second harmonic. This is just an example, but you could define a second harmonic disturbance on the direct voltage. It could look like this. I would like to have this disturbance be equal to 5% of the rated DC voltage. I just rerun the collocation methods, and I can observe the results in the time domain with the plot function. So you see that the waveforms are slightly different. I can this time plot the direct current, the direct voltage. Indeed, I have to define it as a cell, because otherwise it doesn't work. And we see indeed that this is essentially a constant value, which is very close to 2.5 after scaling. And then we have this ripple, second harmonic ripple on top of the direct voltage. I will remove this line for now.